This is Aaron Acee, and this is the 9th video lab report, Physics 2211, where we had to analyze the motion of a mass at the end of a spring. It's also acting like a pendulum. So the first thing I did, I took the video that Dr. Greco gave us and analyzed it in Tracker. So the first thing I did was I oriented the axes to where the origin was at the point where the spring is connected to the hook. Next thing is I made a calibration stick because the length from the origin to the center of mass of the mass at its initial position was 70 centimeters. So after that I started tracking the mass as such. So after I did that, I extracted the data and plugged it into the Python program here that we made last week in the AtLab. So last week we just analyzed the motion of a mass oscillating up and down with no horizontal movement. So this week we do have horizontal movement. So the only difference between this week and last week was that the initial x component position last week was 0, but now we actually have an initial x component. And that's the only difference between this code and last week's code, was the initial position. So after I ran this, I got something that looked like this. And the graph of this, of the exponent in time, looked like this in Python. In Tracker, it looked very similar up until, say, 2-3 seconds, because this is a very initial position dependent system. So any little change in the initial position can cause a drastic changes in the later position versus time graph. Also, work was done in the where the hook connected to the spring. Work was lost, or energy was lost due to friction. So that takes to what does it mean. The first one is compare the period of oscillation you found from examining the x component of position with the period of oscillation determined from the y component of position. I found that they were the same in this, and that would only be just a coincidence, because the period of oscillation of spring is square root of m over k, as where the period of oscillation of a pendulum is square root L over G. So I found that in this situation they were the same, just because the numbers worked out. But if it was given an initial stretch of a lot more or a lot less, they would not have been the same. So the second question is, with your new choice of system, determine the work done by the surroundings. So our new system consists of the spring, mass, and earth. So the only work done was just by the friction between the hook and the spring. So the energy principle is still satisfied, because where energy was not destroyed or anything, it was just lost to the surroundings. Okay, so that's now the third question is, when defining the gravitational potential energy in your computer model, you made a choice for the location of the origin. When you change the location, does this affect the system? It would change the gravitational potential energy, because the delta y or h from gravitational potential energy of mgh would change. However, basically just the numbers would change. There would still be the energy in the system would still remain constant, but just the number of that would change.